Hi everyone, welcome to Daily Data Structures. My name is Abhinav Singh, and today we will be continuing our discussion of algorithm analysis. So today I'll briefly recap big O notation and discuss the limits of that piece of information on its own, and then we will augment that information by discussing omega and theta notation. But before we do all of that, we must really understand what a lower and upper bounds really are. So, to quickly recap upper bounds in big O notation, recall that if you choose a constant c and a constant n, and show that f of n is less than or equal to c times g of n for all n greater than or equal to capital N, then f of n is in big O of g of n. The limits of this piece of information is really that it only gives you an upper bound on f. So, the statement that n is in big O of n to the 20 would be true, but that doesn't really tell us a lot about the runtime. As a result, big O notation has the potential to be misleading by itself. So, to fix this, we also discuss the lower bounds of a function. Let's continue with our example from last time, where t of n was equal to 20n and f of n was equal to 200n. We showed last time that t of n was in big O of f of n, if we pick c to be equal 1 and n to also equal 1. So, that showed that f was in the upper bound of t. However, the opposite can also be true when we say that t is the lower bound of f. This insight is incredibly important, and that is the basis for omega notation. If f is the upper bound of t, then t is the lower bound of f, and so we get the following definition, which is literally the opposite of big O notation, and that's called big omega notation. It reads the following definition. Omega of f of n is the set of all functions t of n that satisfy the following condition. There exist positive constants d and n, such that for all greater than or equal to capital N, t of n is greater than or equal to d times f of n. So big O tells you an upper bound and omega gives you a lower bound. So if we had a function n, we can easily see that n is sandwiched in between n squared and 0.5n for all n greater than 0. So we can make the following two statements, that n is in big O of n squared and n is also in omega of 0.5n. The thing to take away from all of this is that big O tells you that your algorithm is at least this good, and that big omega tells you that your algorithm is at least this bad. So another nice tip for doing a lot of these proofs, especially one for omega proofs, is to prove that t of n is in omega of f of n, then all you need to show is that f of n is in big O of t of n, just like we discussed above. If a function f is an upper bound of g, then g is the lower bound of f, just like we talked about 2 slides above this. So let's take an example and walk through this. Let's let f1 of n equal 100n and let g of n equal n, and let f2 of n equal 0.5n. We can easily see that g is sandwiched in between f1 and f2. Ergo, we can also say that n is in big O of 100n, because 100n is the upper bound of n, and we can also say that n is in omega of 0.5n, because 0.5n is the lower bound of n. However, also notice that f1 of n and f2 of n literally differ from g by just a constant. So, if we write the following compound inequality, 0.5n is less than or equal to n, which is less than or equal to 100n, we can notice that if we pick c to be 100 and that d to equal 0.5 and capital N to be equal 0, then n is in big O of n, and n is also in omega of n. And that is the basis behind theta notation. The definition of theta notation is the following. A function f of n is in theta of t of n if it is in both big O of t of n and omega of t of n. So from above, we can say that n is in theta of n because it is in both omega of n and big O of n. Theta is the best way to tell how good an algorithm is, because it contains information about both the upper and lower bound. N is not in theta of n to the 20 because n is not in omega of n to the 20, whereas above, when we talked about big O notation, we could say that n was in big O of n to the 20. So let's talk about all of this in general and put it all together. and start to picture what's going on. Let's take f of n to be equal to n cubed, and let's take g of n to be equal to 3 times n cubed minus n squared, and show that f of n is in theta of g of n. So I'm not going to do the part of the proof where I show that f of n is in big O of g of n. I'll leave that as an exercise for you to do. However, the logic is the same as what we talked about in the previous lecture. So I'm just going to do the next part, and you can just take that for granted for now. So first we need to show that f of n is in omega of g of n. Let's do that by showing that g of n is in big O of f of n, which is that tip that I described above. So we can write the following statement. 3 times n cubed minus n squared is less than or equal to 3 times n cubed for all n greater than or equal to 0. The reason why I can say that is because if we take away the thing that's subtracting from the main component, then obviously that without the n minus n squared would be bigger. So if we take c to equal 3 and capital N to equal 0, then we can see that g of n is in big O of f of n. Ergo, the above claim is true. As a result, we can say that f of n is in theta of g of n. The thing about these proofs is that you need to modularize it into two parts. Show that f of n is in omega of g of n, and then show that f of n is in big O of g of n. So I made a nice illustration to demonstrate exactly what's going on. This is a picture that I made in MATLAB, and I took those exact same functions, but augmented them with constants. So I took c to equal 100 and d to equal 1/4, and I showed f being sandwiched in between 100 times g and 1/4 times g. F is in red right here. 1/4 times g is in blue right here, which is the lower bound, and 100 times g is green, which is right here. So this shows the upper bounds and lower bounds of f, and shows you exactly why theta notation is a good description of the runtime. So now we can talk about the consequences of theta notation. Theta notation is the best way to describe your algorithm. And one final thing before I leave you is with the following warning. Big O is not the same as worst case running time, and big omega is not the same as the best case running time. They're just bounds on your algorithm in order to describe it. Often, I find that people get confused about these two ideas, so I wanted to clear that up. I can find bounds on anything, but it doesn't mean that these functions are the best case and worst case running times. However, big O and big omega and big theta are great ways to express the runtime in general.